Well, I guess it's time for another devlog. So in the previous episode, I showcased the implementation of the A Pathfinding that I use for the movement of my NPC that you can see right here on the left side of the screen. But I ran into a problem that made me scrap the whole A pathfinding and basically start implementing my own thing, simply because I cannot really easily handle pathfinding with this sort of algorithm whenever the NPC is not visible in the current scene. So what I ended up doing was implementing Dijekstras Algorithm, which is, first of all, an algorithm that has a name that's hard to pronounce for me. And second of all, it is a pathfinding algorithm. And it's used in, for example, navigational systems, but obviously in a modified version. And its purpose is to find the most efficient route from a start node to an end node. I have a grid graph over here, which consists out of the node A to F. All of these nodes have connections and a cost displayed over them. I have a table with a column node, and I'm gonna fill them up in the alphabetical order. So I have node A, B, C, D, E, and F. We have a cost and we have a previous node. And maybe you are asking yourself, well, now I have a grid graph, but what do I actually do with this graph, or what would this graph represent if I look at the real world, or for example the game development? Well, for real world examples, you could say that these are houses and this is a street, and the cost of the street would be calculated, for example, by how big is the street, how much traffic is on the street, is it a highway or is it a road in a city, how fast can you travel, and so on and so forth. For the game approach, like what would this represent in a game? Well, obviously, or not obviously, but these nodes would represent coordinates in a system that you would set, which would then be your waypoints, and the cost would probably, at least in my game, simply be the distance from point A to point B. So for example, if you have a shop, you have a node shop, and then you have a crossroad, and then you have a distance which is maybe 20 units, and that will be the cost to reach the crossroad from the shop. Just to give you some sort of example what this graph would represent in real life, or maybe in a game development perspective. So in this example, I'm gonna start with node A. And because it's our starting node, to reach this node, I don't have any cost at all, and I don't have a previous node. Because we start at this node, it doesn't cost us anything to travel from A to A. And so now I need to look up which nodes we can reach from point A. So first of all, we can reach point B, and it would cost us 1 to get from A to B. So now I can look into this table and I see node B. I don't have anything yet in this table, and if you would implement it into your code, you would probably assign a cost value to all of the nodes initially, let's say in infinity, just to have a reference for the cost. So to reach point B, like node B, it costs us 1, and the previous node is A. Okay? We do the same thing again. We look up which other nodes can we reach from point A, in this case node E. So we can reach node E from A, and we don't have anything in the table for node E yet, so we write in a cost of 2, and the previous node is A. So now by looking at this table, we already know that we can reach point B from A with a cost of 1. So now I go ahead and I mark my node A that I've already checked all of the neighbors. If you would implement it into your algorithm, you would probably have some sort of list or an array that stores all of the nodes that you've already checked. So now I go ahead and I use, or I take the next node. In this case, I'm just gonna take the one that I can reach with the lowest cost. So this is node B. We can reach node C with the cost of 3 plus 1, because you always use the full cost from the start node, because you have the cost to node the cost to reach node C is not only 3. The because you start at point A. So the cost is 4. We don't have anything in the table yet, so I go ahead and I add 4, and the previous node is B. So I now know that from A, I can reach C through B with a cost of 4. I can also reach node D, and node D has a cost of 7. So we have checked node B. Now I'm gonna start with node E, the next neighbor of node A. We now see that from E we can reach C with a cost of 3. And this is where it gets interesting. So we already have a value, or we already have a way to reach node C through B with a cost of 4. But actually, if we take the route from A to E to C, well, we only have a cost of 3. So what we do is we remove this entry and we say, well, we only have a cost of 3 through the node of E. And then, well, because E doesn't have any more neighbors, we mark this node as completed. Then we check the last node, which is F, and we see, well, we could reach D with a cost of 8. Well, we don't want that. We could reach C with a cost of 11. We don't want that either. So we have all of the nodes checked. We have our table over here. And now with this table, we know that the most efficient way from node A to node F is through node D. We reach node D through node C. Node C we reach through node E. And node E we reach directly from A. So with this table, we can now define from our starting point the most efficient way to any of the other nodes. So I went ahead and I implemented this sort of algorithm into my game to map out all of the nodes, which basically is a recursive method that does exactly what I've just showcased. And then then I have a method create path, which just simply goes through this table and determines, well, the order of nodes, or all of the nodes that we need to reach from A to B. And after a little more, let's say, coding magic, I managed to implement the pathfinding in a way that NPCs, or the position of the NPCs, are calculated and applied to an NPC without having the NPC in a current scene. What I mean with that, the position of the NPC is calculated in the background, and then I check whether the current position is, for example, inside the current scene, and if so, well, I need to show the NPC to the player and do the movement. And you can see that now if it hits 8, the schedule of this NPC is set to watering. So now he starts from in front of the seed shop to move towards the crops. I don't have the tasks yet implemented, so he's not doing any animation, but he's now going from crop to crop, and the next step will probably be to just make him stop and then do the watering animation. The cool thing now is, now he's on the 3rd row. If I now leave the scenery and go to the left side, the NPC is not visible in the scene, but he's still moving. So if I now re-enter the scene and I come back up here, well, when we left the NPC was up here. Now he started down here, walking towards to the right side of this lettuce, and now he's going to finish up with the wheat, and he's going back to his position in front of the seed shop. So I managed to implement the pathfinding successfully. I now need to add the actual animations for the tasks, in this case the watering, and this allows me to, well, do with the NPCs whatever I want. Another thing that you see is what I need to do next is whenever the path ends, or the NPC reaches the end of the path, he should obviously go into the idle animation, and in this case just stop doing the walking animation and look straight down, which will be something that's probably relatively simple to implement. But for this video, I think I've reached somewhat of my limit. So next week I will probably showcase the polished version of my pathfinding algorithm. I hope you enjoyed this video. If you liked it, consider hitting the like and subscribe button, and I hope you have a good one. Stay safe and see you next time. Bye bye.